Assalamu alaikum warahmatullahi wabarakatuh. Welcome to the Matric Revision program. My name is Daniel Matthews, facilitating this lesson today. But I will not be the one teaching you, of course, because this is mathematics and that's one of my worst suits. However, we do Sandra Dickson on board. She has a BSc degree in mathematics from the University of Stellenbosch. Sandra had a successful career and managed her own business. And since 2011, she returned to her first interest, which is mathematics. And so for the past decade, Sandra has been assisting grade 8 to 12 learners with one-on-one extra math classes. Good afternoon, Sandra. How are you?
Good afternoon. I'm very well.
That's good to hear. Now I got a little bit confused in regards to morning or evening. Whenever it gets 12, I always get that confusion. However, Sandra, I've done a little bit too
No
much
problem.
talking. Why don't you take us away with a lesson?
Okay, thank you very much. Right, good afternoon. Today I'm going to do Euclidean Geometry, which is basically a follow-up from the lesson that I did a week or so ago. So if you look for the previous video, on that one, I did the Euclidean geometry, but basically the circle geometry, which is given in grade 11, right? So in other words, grade 11 pupils that battle with circle geometry can maybe have a look for that video and watch it, because what I've done is I go through the 9 theorems there as well as its proofs. And I really try to explain those theorems to the best of my ability. Now, today I'm continuing with more Euclidean geometry, and that is going to be, again, some theorems, because we are now moving on to the grade 12 stuff, which includes 3 new theorems. And at the end, I'm going to do 2 basic problems to illustrate the use of these theorems. Now, just as a matter of interest, the grade 11 circle geometry and this geometry makes up a third of paper 2. So therefore, it is of critical importance that you guys must master this. Otherwise, you will really lose a lot of marks. And what you need to be careful about, or maybe understand, is give yourself some credit that you've worked hard through the years. This is a very difficult part of mathematics. However, the papers are normally structured in such a way that there's pieces and questions that's really elementary. So it's important that you read your paper very well to find those questions which are really easy to answer, and maybe recognize the more difficult ones and not waste your time when you rather could have done some other sections of paper 2. However, let's get going. Now, basically, the grade 12 Euclidean geometry is all about proportionality and similarity. So the first theorem here is that if you have a triangle and you draw a line parallel to one side of that triangle, that line divides the other 2 sides proportionally. Now, I will go in a lot more detail with pictures to explain this. Now, the second theorem that flows from this first one is the midpoint theorem. Now, that one you also did in grade 11, and it's actually a special case of the theorem that I've got above. So the theorem above says any line parallel to one side of a triangle divides the other 2 sides proportionally. Now, the midpoint theorem, with that one, that parallel line is basically in the middle of 2 of the sides. So therefore, you will have 2 sides of a triangle split in the middle with a parallel line. And then there are various deductions that you can make out of that. But I'm not going to go into that today. The third theorem, corresponding sides of two equilateral triangles are in the same proportion. Therefore, they are similar. Now, what this boils down to, if you have two equilateral triangles, but with similarity, these triangles are not equal in size, right? So they have the same shape, but not the same size. So if all the angles are equal in these two triangles, we can therefore deduce that they are similar and the opposite sides are in proportion. So this is the English around it, and I'm going to put up the short version for Theorem 1. So if you use it, please remember to write that short bit, the line parallel to one side of a triangle. That is enough. And please write it, because that could get you at least 1 mark, because inevitably, if you have a problem of this nature, that would be one of the reasons that you would use. And then at number 2, we would write midpoint theorem, and there's also a converse. And then with the third one, you would write corresponding sides are proportional, which indicates similarity. So that is just an English background as to what this lesson is all about. Now let's look at the first theorem. And I'm repeating there at the top. A line parallel to one side of a triangle divides the other two sides proportionally. So let's look at the parallel line. So this one line, parallel, so that's DE, is parallel to BC. So if you do any problems that looks like maybe it's this section of the Euclidean geometry, look out for your parallel lines. So if you have a triangle and there are these lines. So DE is parallel to BC, and I'm going to do the proof now following this slide of this theorem, and basically then AD to DB is in the same proportion as AE to EC. So normally the way we talk about this, so to have the mathematical language correctly, we will call AD a short side and DB a short side. And if we talk about AB, the complete side, we will refer to it as a long side. Now, why I'm telling you this is that the basic of this theorem is to say that AD to DB is equal to AE to EC. But we can also do AB, a long one, to a short one, AD, is the same as AC to AE. So I strongly suggest that you maybe read up on this so that you can see exactly what what we can also do with these ratios over here. So let's explore this theorem. Now, before we can explore it, there are two very important concepts that you need to understand, because this is used when we prove this theorem. So here on the left-hand side, triangles with the same vertex, in other words, A, the same vertex. So angle ABC and angle ACD, these two triangles have the same vertex. It also has the same height. Right? So there's the height. So it's pretty important, because some of the most difficult questions hinge around this concept. But they do not ask this every year. However, you need to understand this if the proof for the theorem is asked. So I'm just repeating here. Triangles with the same vertex has the same height. And it's the perpendicular height. Right, so let's just go over it. What does it say? So if we have triangle ABC, its perpendicular height is over here. The second one is a little bit more difficult to see. Triangle ACD. Now this height won't fit in here. So it's on the outside of the triangle. Right, so the height is not part of the triangle the same way as in ABC. And that makes it pretty difficult to see and to understand how to apply this. Then the second thing that we do, triangles with a common base. So here BC is a common base to triangle ABC and DBC. So if you have a setup where two triangles has a common base and you have two parallel lines, the areas are equal. Right? So if we worked out the area of ABC and it was, say, 10 centimeters squared, and we work out the area of BDC, it will also be 10 centimeters squared. So again, it's very important to understand this and this. It's not really theorems. You don't need to know the proof, but you need to recognize and understand it. Right, now let's jump into the proof of this theorem. So again, DE is your parallel line to BC, and we want to prove that AD to DB is this in the same proportion as AE to EC. Right? That is what we want to prove. So to do that, we will construct H1 from E to DA perpendicular. So we have H1. So now, and this is where you need to latch on to my previous slide. If we look at triangle ADE and we look at triangle BDE, can you see we have the setup? And I'll just go back. We have this setup. And that is what you need to understand when you study this theorem. So we have AED, that's got the perpendicular height H1. And we have this green dotted triangle with a perpendicular height that sits outside. So it's basically the previous slide turned on its head. But one need to understand that. And what I've done is I've taken it out of the proof because the next slide is pretty complicated because then the whole proof is there. So I've just taken it out so that you guys can see what's happening. Now, when you study this, we work with the areas. So we take the area of triangle ADE, the top one, and we work out the area of triangle BDE. And the formula for the area of a triangle is half times the base times the perpendicular height. See, so that is what I've got here. So it translates into a half times AD times the perpendicular height. And the area of BDE is a half times its base is DB times its perpendicular height, which is over there. Then we can cancel the two halves and we can cancel the two H's. And we are remaining with AD over DB. So let's have a look. Where in the picture is this? AD is in proportion to DB. Now, I just want to stop for a second that AD, if they give it to you in a fraction like that, that means it's in proportion. They can also give it to you like AD colon DB, but it means exactly the same thing, and we'll see the use of that a little bit later. But just understand from here is that there's a couple of ways of depicting that. Right, so here's the busy slide I was talking about. So at the top, I've got again, what are we trying to prove? We're trying to prove that the line parallel to one side of a triangle, so again, that DE, which is parallel to BC, divides the other two sides, AB and AC, proportionally. So to do the proof, and we've seen on the previous slide how I simplified it, so I'm just going to do it all in one now. So we will draw H1 from E to AD. And we'll call it H1, and it is perpendicular. So exactly like my previous slide. And if you forget how to do it, the way I remember it is that we start in the corners here. So the one, you start E and it goes up there, and you will now see that the other one is from there up to there. So we repeat what's on the previous slide. Once we've done this, we can say that the area of ADE divided by the area of BDE is equal to half AD times H1, and BDE is half DB times H1. And like on the previous slide, we cancel the halves and the H's, and we're left with AD to DB, or AD over DB. Now, similarly, we obviously now have to continue because we've done this side. We now have to bring this proportion into the proof because they are equal to each other. So we will draw H2 from D up to AE, and it's perpendicular, and we'll call it H2. So we do the same thing. So now you have to look from the other side of the picture. But we still use the top triangle, ADE over DEC. See this other triangle? And we do the same as with what we did with H1. So a half AE times H2 over a half times EC over H2. And similarly, we get rid of the halves, we get rid of the H2s, and we remain with AE to EC. Now we need to link these two things together because we want to prove that AD to DB is equal to AE to EC, like we set out to do there at the top in the beginning. So let's look at what we have. If we interpret these two things, we will see that at the top we have ADE, and in this one we have ADE again. So that is equal to each other because it's the same thing. And then here at the bottom, triangle BDE, the area of triangle BDE is equal to the area of triangle DEC. Let's have a look in our picture. So here's our parallel lines. And you can see from my previous two slides back that these two triangles, DBE and EDC, have the same base, and they are between parallel lines. That is why we give the reason DE is parallel to BC. We could have added in there same base as well if we wanted to. So therefore, if we could say that this is equal to this, because why can we say it? Just to repeat, that is equal, the ADEs, triangle ADE, and we've just said that triangle BDE is equal to triangle DEC. So as a whole, this is equal to this. And that is what I've written down here. Now, because this is equal, we can then conclude that AD over DB must be equal to AE over EC. And so we've proven the theorem. So it is difficult. They do ask this quite a bit, and it's around about 5 marks. So please study it and make sure that you can reproduce it exactly like this, or maybe the way it is done in your textbook, because the textbooks do vary slightly, but the gist of it is the same. Now the next theorem, the similarity one, here they will give you a picture of 2 triangles, but they'll give it to you without the red. Okay, so in the question, you will have these 2 triangles, and they'll either mark it like this, that angle A is equal to angle D, angle E is equal to angle B, and angle F is equal to angle C. So that is given. So they'll either mark it like this, or they'll tell you like at the top. Now they want us to prove that AB to DE is equal to AC to DF. Now, what is the significance of this? Because it took me a while to understand how do you tie this in with the problems later. But the problems around this hinges around usually a complicated picture where the triangles are intertwined, and you need to find whether they are similar or not. But because this is a theorem, it's done in a pretty straightforward manner. So let's see, how do we do it? So we need to construct, because we need to link up these 2 triangles. So we will construct AS, the same length as DE. So what we're doing is we're taking this triangle and we transferring it into the big one. Why can we do it? Because if we move this one here, it's going to fit perfectly because of the 2 angles that's the same. So in the way we do it, we transfer it there and we construct AS equal to DE, and we construct AT equal to DF, and we can mark it. That says it's equal. The 2 sides are equal in length, and those 2 sides are equal in length. But now we just have an arbitrary line here. So to use the theorem, we need to prove somehow that this line is parallel to that line, because then we can use the previous theorem to make a conclusion. Now, once we've constructed it, we need to show that these 2 triangles, this small one, AST, is congruent to DEF. All right? And to do that, we have a side, and we have a common angle, and we have another side. So in the congruency rules, we are using side, angle, side to conclude that these 2 triangles are congruent. And by congruent, we mean they are exactly the same. In other words, the same in shape and the same in size. Now we can say S1 is equal to angle E, because we've just proven congruency. So that angle must be equal to that angle. But we also know that angle E is equal to angle B. So again, we have the concept that if S1 is equal to E and E is equal to B, we can conclude that angle S1 is also equal to angle B. Again, like I've mentioned in my previous video, that this is like your two-step deductive reasoning. So we can't straight away say that S1 is equal to B. There's a step in between. So just to repeat here, S1 is equal to E from congruency, and and E is also equal to B. Now, if we have that situation, that S1 on the picture is equal to angle B, we can now conclude that ST is parallel to BC because we have corresponding angles here. S1 and angle B are corresponding angles. And because they're equal, we can conclude that this is parallel. So now once we have this parallel line, we have the theorem that says if a line is parallel to a third side, it divides the other two sides proportionally. So from these two parallel lines, we can conclude that AB, the long one, to the short one, to AS, is equal to the long one AC over AT. And we use the theorem and a deduction from the basic theorem. Remember, and if you've forgotten, just go back and have a look where I explain the idea of long sides, short sides, just so that we know what I'm talking about. So now we know that's the case. So therefore, AB to DE, because we're basically replacing DE, or we're replacing SA with DE, because that's the way we constructed it. So we are basically just replacing AS with DE and AT with DF as we've constructed it. And there we've proven what they've asked. Because this section of the Euclidean geometry in grade 12 has got very few theorems, therefore you will have to know the proof of both of these theorems, because they can put 5 marks in the bank and you go away smiling. But it's difficult concepts, I understand, but don't switch off. Just watch my explanation once or twice and write it down while I'm talking so that you practice it 2 or 3 times, and then you will remember it. Right, now, once we have the theorems, we go into the problems. And they are also pretty difficult. Right, it is difficult in the sense that it is concepts that is not really, it's difficult to wrap your head around it. However, please don't laugh, but they were trying since grade 7 to teach you guys this concept. So let's see, how does this work? If we have a line of 21 centimeters, AB. So now remember, now it is centimeters. And we are working with proportionality, in other words, ratios. So now we want to divide this line in proportion 4 to 3. So in other words, we want to cut this line up like that maybe. And this bit, AC, would be 4, but not 4 centimeters, Because if we said it was 4 centimeters and we would say CB is 3 centimeters, we would not get to 21. You see the problem? So when you do these problems, you need to clearly understand the difference between a ratio, which has got no units, and actual centimeters, meters, millimeters, or whatever they're giving you. So how does this work? So we want to split it AC to CB. But we want to know now, if we take a guess, this side must be longer than that one. So let's take a wild guess. This could be 10 centimeters and that 11 centimeters. Just a guess. And I'm doing the guess just to show you guys that we need to, our answer need to be in centimeters, but we're going to use this ratio or proportion to actually do the calculation. Now, when you do these problems, in order to separate the ratio from the centimeters, we suggest that you use a letter, a P or a K or a T or anything. So basically we can say AB is 4, but by now you must know it's not 4 centimeters, it's 4 something. So 4P. And the other bit, 3P. And if we know what P is, we know the centimeters of each of those lines. So we will start off by saying AB equals 4P plus 3P. And plain algebra, AB is 21 centimeters. We replace AB with 21 centimeters equals 4P plus 3P. Because it's P's, we can add it up. So 21 centimeter equals 7P. So therefore, if we divide by the 7 on this side to get the P alone, P would be 3. So now we know what P is. So we can work out AC. AC is 4P. So it is 4 times 3. So AC is 12 centimeters. And CB is 3P, 3 times P, which is 3. So CB is 9 centimeters. So please remember this concept when your problem has centimeters or meters mixed up with ratios. Right, then we will use this concept. Example 2. We have a triangle and we have DE parallel to BC in triangle ABC. AB is 28 millimeters, and here's our ratio. AE to EC equals 4 to 3. Determine the length of BD. So basically we have, if we transfer this top, and again I stress, when you do problems, you cannot just jump and read determine the length of BD. You have to read everything at the top because this is where your information is. In all geometry, you need to read the description and transfer the description to your picture. So let's see, let's transfer it. So AB is 28 millimeters. AE to EC, the proportion is 4. And the minute we work with proportions, we will bring in a letter, so 4K. And the reason for that is hopefully obvious to you by now, is to distinguish so that you don't confuse the millimeters with the ratio. Okay, so AE is 4 and EC is 3K. So that is how we would put the ratio onto our picture. And then it's important to know that we can add it up. So 4K plus 3K gives us 7K. So AC is 7K. So let's see how will we do it. If we use our theorem, a line parallel to one side of a triangle, we can say that BD to BA, so it's a short to a short, is equal to EC to CA. BD to BA. So it's a short to a long and a short EC to a long. And that is important that you understand that there's various flavors of this. So this is a short to a long and a short to a long. So now we just fill in. We need BD and AB or BA is 28 millimeters. We fill it in. Equals EC is 3K over CA is 7K. So we have BD over 28 equals 3K to 7K because we've basically substituted what we knew into that. Then we use cross multiplication to solve it because we want BD. We want the length of BD. So BD times 7K cross multiplication. Basically how you would see cross multiplication is you are getting rid of the fraction. And we do it by doing cross multiplication. So BD times 7K is equal to 28 times 3K. We want BD, we want to know the length of BD, so we get BD alone. So we have 28 times 3K divided by 7K. You can see the K's cancel out because that is normally what happened to the letters. They cancel out or you work them out, but in this case they cancel. And 28 times 3 divided by 7 is 12 millimeters. In other words, BD over here is 12 millimeters. Right, so that is a fairly simple application of the first theorem. Now we have a slightly more difficult question, and we are using the third theorem, which is similarity. So just bear with me and let's see how we fare with this one. Now in triangle PST, the big triangle, we have TS perpendicular to PS. So this whole angle here is a 90-degree angle. And RQ, this one here, is perpendicular to PT. So the 90-degree is this whole angle here. All right, there's your 90-degree. So the first question is, prove that triangle PRQ is similar to, so it's this small triangle, is similar to triangle PST, which is your big triangle. So what I would normally do, and I still have to learn how to do it on the slides, is to color this and maybe to color that just so that you can see which triangles we are working with. Because we're doing similarity, we need to do 3 angles. But 2 is enough, but I did 3 for completeness sake. Now, something that you need to know about the similarity problems, and this is one of the questions that you must get, and they ask it in every single paper. You will see this type of a question, and you must be able to do this. This is one of the less difficult parts of this math. Now, what you need to understand when they tell you that two triangles are similar, basically it means that the angle at P must be equal to the angle at P, which must be your common angle. So let's see. If we have the small triangle and the big triangle, can you see that angle P is common? So we can write down angle P is equal to angle P, and it is the common angle. Then we need to know that the angle at R must be equal to the angle at S. Right, so the angle at R in the small triangle is R1. And the corresponding angle in the big one is S1 and 2, which is 90, and R1 is 90 as well. Because of the straight line, because that's 90, that has to be 90 as well. So if one wants to see how the similarity would be, one has to take triangle RPQ and transpose it so that R1 falls on S1 and 2. And then you'll see that this one fits inside the big angle, the big triangle. So we can say R1 is equal to S1 plus 2, given 90 degrees, because I told us they were 90 degrees. And then for completeness sake, the angle at Q must be equal to the angle at T. So the angle at Q must be equal to the angle at T. Now, you may see clearly that it's not going to be that easy to prove it. But the third one's reason is always the sum of the angles in a triangle. Because for similarity, we need to find only two angles that's equal. And then by definition, the third angle will be equal as well. And we've proven our similarity, so therefore we can say that triangle PRQ is similar to triangle PST. Now, they may either ask you to prove this, or they may tell you in the question that this is the case. Now, very, very important. If you see this, and I've written it big here, if you see this type of a situation, we can immediately write down this proportionality. Because the triangles are similar, their sides are in proportion. So we can say PR divided by PS. So the first two letters is equal to the ratio RQ to ST, the last two, is equal to PQ, first and last, and now you can guess PT, first and last. So whenever you do these type of problems, and you have no idea how to answer the question, if you see this, write that down, okay? And you will get some marks. I should actually, the reason here is because of similarity. Right, so we've actually answered the question here already, but I'm just showing you that once you get this far, remember this always flows from that step. The second question, it's still the same drawing, B. Now they want us to prove that RQ 2, and this is your ratio proportionality. They also could have written it as RQ divided by PQ. But here we've used the 2, so RQ to PQ is equal to ST to PT. Now this may look like Greek to you, but you must please recognize when they ask this type of a question, it is similarity and you need to find two triangles that's similar to each other. And because I chose a fairly simple example to explain this concept, I've used from A, because this tells us it's got to do with similarity. We need to find this type of a setup, PRQ similar to PST, which we've proven in A. And we would write down what I just told you on the previous slide. The first two PR to PS equal to the last two RQ over ST equals PQ to ST. Now from this, we need to match. So we look at our question and we see there's a RQ in the question, there's a PQ in the question, there's a ST in the question, and a PT. So we only need this blue shaded part to get to our answer. And proportionality like this, we can multiply them at the top, or we could use, not multiply, we use the ratio of the top, because we can rewrite this in numerous ways. So therefore, from here, we can say RQ to PQ, the two top ones, is equal to ST to PT. And we've done what they asked. A complex concept, but not that hard if you recognize the problem and understand that this leads to similarity and similarity leads to this, and then you match your sides to get to your answer. Let's look at another example. Now, please note the colons here, because this with a colon is the same as writing it as a fraction. Okay, it's just a different way of writing the same thing. Now, in the C part of this question, can you see now we don't have colons anymore? Now it's a multiply. Now they want us to say or to prove that the side PR times PT is equal to PQ times PS. So please familiarize yourself with whether there's a colon or whether there's a dot, which is a multiply. So again, when you see this, you know it points to similarity. So we use our similarity from the A part of the question. And we will again write down the first two PR over PS over the last two RQ over ST, and first, last, PQ over PT. The same as in the B part. And now we match again. So now we see, in the question they're talking about PR and PS. And they talk about PQ and PT. So this time we will need this part of the equation, and we can discard this. Because it's a multiply, we're not working with ratios now like in the B part. We can do cross multiplication. So PR times PT is equal to PQ times PS. So in the B part, we worked with a ratio, and we continue to work with ratios. But when we work with a multiply, we work with cross multiplication. Again, I think it's a difficult concept, but if you recognize that when you see this in a question, they actually want you to find two similar triangles in the picture. Once you've done this, you write down this piece, and then most of the time, it's basically matching with a question to get to your answer. Right, guys, this concludes the session for today, and I hope that I've made this part of your Euclidean geometry a little bit more clear. However, it's practice, 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 and I'm just stressing again that it makes up a third. In other words, 50 marks of your 150 marks of paper two in your uh, now in your June, no, sorry, June is past, in your September and November exams. Bye bye and happy learning.
Thank you so much, Sandra, for coming on board and enlightening all of the views. I'm sure many of the students are much, much better off after this enlightening tutorship lesson. Thank you so much for coming on board.
Pleasure and bye bye.
Bye bye. To all of our listeners, also bid you adieu. That brings us to the conclusion of today's lesson. Tune in tomorrow and we'll have some more Matric Revision. I believe it may be either English or Afrikaans. We'll be starting with that. Tune in tomorrow in the afternoon and we will have that broadcast going. But from my side and the rest of the Voice of the Cape, I bid you Assalamualaikum warahmatullahi wabarakatuh. See you tomorrow. Inshallah. Ameen.